software systems are incredibly complex, especially when you go out of a single main node, when you look at distributed systems, network systems, and even AI systems, right? So these are incredibly complex as such, and people who build those systems want to ensure that they are in fact correct. Number one, and number two, they're performant, right? So instead of waving your hands and sort of just hoping for the best, we could. There are indeed approaches you could sort of adopt to ensure that the systems you build are correct, or they have, in fact, the properties that you want them to have, and also they're performant, right? So, how to do this rigorously, using formal mathematics, and how to do this automatically without engineers having to spend their time sort of writing proofs and all of those things, is what we do in the lab, right? So that's succinctly speaking, that's what our research in PLV is about, right? So V in PLV stands for verification. So verification is essentially verifying that your systems actually do behave the way you want them to behave, and it's not same as testing in the sense that you write a bunch of test cases, but that's not verifying your system because you might have missed a few cases and so on, right? So verifying is essentially sort of mathematically proving that your system behaves the way that it's supposed to behave, and more importantly, doing so automatically, right? Okay, so here are the bullet points, showing sort of a few projects that we currently are active in our lab. So I listed them here because they sort of give an idea of the things that they refine the theme that I mentioned there, and they give an idea of things that we actually work on, right? The first thing is correctness and incorrectness logics for event-driven systems. For example, all of you have smartphones in your hands or in your pockets, and these are the applications, the apps, the so-called apps, are essentially event-driven systems, right? So there's iOS or Android that's running behind the screen and sort of keeps sending signals, and your application essentially reacts to those signals, right? So for those of you who programmed in JavaScript, who are unfortunate enough to program in JavaScript before, you might have known that there are callbacks, and you can quickly devolve into callback hell. So you don't know what order these things are executing, and so when a crash occurs, your sort of stack callback, your error stack essentially shows you only the recent callback, but not your history before, right? So then, how do you sort of diagnose these issues? How to do this automatically? And once you sort of conceive a fix, how do you prove that this fix, in fact, will actually fix the issue, the underlying issue? So those things require a very novel approach to reasoning about programs, and that's what we've sort of working on this. We recently graduated a student called Sean, so he was essentially the lead on this project, right? So we've gotten some tremendous results there. We published last year in UPSLA. The second is safety and privacy verification for network systems. So as I begin the talk mentioning the distributed systems, network systems, right? So these are without any need for, without introducing any AI into the picture, they are already really complicated, right? So you have systems that are spanning the entire globe. The distributed systems that are geo-distributed. So how do you ensure that these are safe, as in they actually are robust? And how do you ensure that, more importantly, that the data that is there on the systems is in fact private, right? So you don't accidentally leak the data and so on. So guaranteeing those things mathematically is in the realm of things that we do. In fact, this is a project of or area of interest for cloud providers like AWS and Google Cloud as well. So AWS have similar projects similar to this in their realm, actually. And foundation of cyber physical systems. So I'm going to give an example of that. So what do we mean by cyber physical system and why it's important to ensure that they are? But the short answer is because these are physical systems, these are not just cyber ones. These are they control actually some physical devices. So you want to make sure that the robot you bought for your Thanksgiving sale is not going to kill you, right? So someone an automation plant is not going to just sort of increase the uranium inside the nuclear reactor and just sort of blow it up. Right? So you want to ensure that these things don't happen, and testing is not enough. You want to sort of do full mathematical proof, and that's where cyber physical systems come in. Right? Provably safe reinforcement learning is another area of area of research where a lot of progress has happened in the recent days and the recent years. So the idea is to not just do reinforcement learning. I'm assuming folks are at least familiar with the concept of reinforcement learning, where you sort of give rewards to reinforce actions of a bot and make it learn to do certain tasks, like for example, playing a game, right? So insofar as you're just playing games, this approach is fine. But what about things that you're, let's say you're trying to train yourself driving car and so on, right? Using reinforcement learning. How and you want a certain safety guarantees to happen. For example, if the pedestrian, if the camera detects a pedestrian, then your car has to come to a gradual halt, with a few such a distance to spare before the pedestrian, right? So all of that you could write it as a like a specification, but how do you sort of turn this specification into sort of scalar rewards so that your reinforcement learning engine is incentivized to not crash into a pedestrian, right? So how do you go from your high level properties to actual rewards in a provably safe manner? That is something that's what provably safe reinforcement learning is about. And Professor Trivedi, who's right now on sabbatical, so he's the one who primarily works in this area. The last thing is just like a fun little project that I have started with summer undergraduate students. And to my pleasant surprise, they actually made a tremendous amount of progress there. And so we're about to wrap this up, and I'll explain that one as well. Okay. So any questions at this point before I delve into a little more detail about a couple more of these projects? Okay. So here is one example of the project that falls under the bullet number 2, which is safety and privacy verification for network systems, right? So this is the lead here is my student Kirby Lundell. So this came up during discussion with Professor Eric Wustrow, and Professor Wustrow mentioned that TLS has this. TLS is basically the encryption protocol, or the HTTPS protocol, essentially, right? So it's the protocol that guarantees your privacy on internet, right? So once you sort of establish a connection with Google or Twitter via HTTPS, the S there stands for TLS. So the rest of your packets are in fact encrypted, right? So TLS is the protocol that guarantees that. And the unfortunate aspect of TLS is the original handshake, where you actually negotiate the connection to your google.com or Twitter. That's not encrypted, right? Once the connection is established, then your data is encrypted, right? Which is great, but not that great, because now censors, the state actors, the Great Firewall of China or something, so they can actually look at these, the handshakes and prevent your connection from happening to restricted domains, right? Let's say, for some reason, some terrorist state does not want you to access us.gov, for example. They can just block because they can look at the server name indication SNI, right? So to address this, to prevent censorship, so TLS committee have come up with a new standard called Encrypted Client Hello, which has a lot of detail. I'm not going to go into the entire detail, but the code just is, there's a proxy in between, like for example, Cloudflare or so. And you have the original handshake is also encrypted, and because you know the keys of the proxy, it's sort of well known, and the proxy sort of decrypts and actually forwards your request to the final server, right? So this is the idea. TLS committee, the web committee, have come up with the standards. They have published a standard, and people have written few implementations and all of those things, right? But does it really guarantee privacy though? Like, as in, is there any way, despite encryption, that you are contacting google.com and your friend is contacting twitter.com, somehow sensors can simply know that you're contacting different things and ban you, right? So is there still a way of doing that? So that's essentially, in other words, is there a way that sensors or whoever is sort of observing your traffic can distinguish your traffic from someone else's traffic, right? So that's, ideally speaking, they shouldn't be. We need to have something called indistinguishability, which is a probabilistic property. So if you sort of write down this TLS encrypted client hello as a specification, or in fact as an implementation, in fact, not just a specification, and try to verify this indistinguishability probabilistic property, to our surprise, we found out this in fact doesn't guarantee indistinguishability. That is, sensors can still find out that you're in fact contacting twitter.com versus yahoo.com or google.com, right? So what we did is, the way that we were able to find out is by trying to do a mathematical proof that in fact guarantees indistinguishability, and failing to do that proof, right? So then we investigated the reasons why we were able to not complete the proof, and with that we came up with a set of recommendations that we actually sent to the standards committee, right? So certain things have to be padded to the same length, and several hello extensions must always be sent in the same order, and such, right? So there are things that are, like, we found out things that are addressed in the spec but not actually implemented in the actual implementations, and there are things that are not even addressed in the spec. So we sort of made recommendations of what to include in the spec and so on. Okay, so that's sort of a very systemsy project, but nonetheless a problem where this concept of mathematical proof actually helps us, right? I see a hand being raised. AKA Sai Lalit.
Yeah, Professor Gautam, my name is Lalit. So my research background is cryptography. So,
I see.
Yeah. So, did you model this particular protocol, at least based on the spec, to a program, or how did you go about finding this particular, vulnerabilities sort of in the protocol in the spec?
So we actually took the protocol and had its executable specification. I refuse to. We sort of hesitate to call it a full-fledged implementation because you cannot actually compile a binary and run it on a machine, but it is very close to an executable implementation. It is we take the specification, write it down as an algorithm that all of that is pretty much close to the code. And once we have that, right, so we have TLS server component, TLS client component, and so on. Then the proof tries to ask that for all executions of server and client, right? Let's say there are two messages or two things that are being sent. Let's say there are two sessions that are happening, one with one server name, the other is a different server name, right? Can an external observer look at the traces of these two things and find out any difference? Can they difference not in the sense of equality, but rather in the sense of probability, right? Is the trace one equally likely with respect to trace two or not? That's the question we ask, right? So that's the proof that we attempt to do, and initially the proof fails, and later, after sort of doing these things, the proof eventually succeeds. That's the strategy.
Makes sense. So it's more, it's more on computation rather than symbolic, I guess.
Oh, you mean the model? Oh, okay, great. So are you talking? So we are actually, it's a very good question. So it's what we do is a combination of symbolic and computation model. That's in fact that's the novelty here, right? Otherwise, just the fact that we are sort of done a protocol verification doesn't itself count for novelty. The novelty is that we sort of combine things from symbolic model of cryptography and computation model of cryptography, so that our model is precise enough to cache these things, but at the same time is not really as complex as a computation model that we have no hope of ever automatically doing the proof. So we call this hybrid model. We are trying to sort of put this on a formal footing, like essentially show exactly how it relates to symbolic and computation models. But good question. This is a hybrid model.
Yeah, I got it. Thank you.
Okay, wonderful. Okay, so the next is the artificial pancreas project. So I think this is more or less done in the sense that this project is never done, but rather it's more or less done in the sense that there was a program that sort of came to its completion, and Sriram and others have managed to deliver great results from this project, right? So the idea is, there are people who have either hypoglycemia or hyperglycemia, right? So some sort of insulin regulation problems. So you could come up with an artificial, or medical device manufacturers can actually build an artificial pancreas and embed it inside a patient's body. But then ideally speaking, this artificial pancreas has to regulate your the blood insulin level, just like your real pancreas does. But there are a lot of complications, right? So the complications being that, the sensors that you use to detect the glucose concentration in your blood, they can be noise there, they may be faulty, there can be delays in sensing the things, and there's also attenuation of signals, right? And also there are, in general, like regardless of the sensors, you still have complexities such as the delay, for example. Like if you increase an insulin level, for example, right now, the blood glucose level does not immediately is going to go down. So it's basically there's going to be a certain lag, and it's governed by certain mechanisms, the biological mechanisms, right? So whatever actions you take now will have a delayed influence on your blood glucose level. So how do you take that into consideration? And how do you take these events such as the patient might have had a high glucose intake food, for example, right now, and so on. So all of these things are complexities, and you want to ensure that your artificial pancreas, in fact, takes all of these complexities into account and still works as expected, in the sense that it does not let the patient go into either hypoglycemia or hyperglycemia, right? So can you guarantee that a particular algorithm or a particular approach that you use in artificial pancreas, in fact, ensures that the patient does not go into hypoglycemia or hyperglycemia, right? So Sriram and his students, they have actually worked on this thing, and there are a lot of, they came up with a lot of novel methods which can guarantee this to a very high level of confidence, right? So with an epsilon error. So I don't know the details, so I can't really go into the details. So, but Sriram will be here, I think, shortly, and he can answer the details for you. This is the small, small as in it has now become a big project, but this is something that we started as a fun exercise, right? So this started when when I taught a course in 23 spring, and students were using ChatGPT to answer their homeworks, right? And since, well, it's okay if ChatGPT is great all the time, but it sort of produces silly errors. And students who have used ChatGPT, all of them have had the exact same errors in their homework submissions, right? So I thought it was somewhat silly because, these are not really reliable, right? So these are language models after all. They are not programming or code models, and also they don't even give a statistical guarantee of whether how often they can be correct, right? So then the idea is, okay, can you sort of language models or generative AI in general is good at generating things, even those things are nonsense. And we have, on the other hand, things such as theorem provers, which are good at detecting nonsense, or that is, which are good at proving that things are in fact right, or sort of showing that they're in fact correct, right? So now the high level idea is, can we put these two things in a tight loop, so that language models keep generating their hypothesis, what they think would come next when they're trying to generate the code. They might think, oh, the next statement should be a system call to discrete, for example, right? So they keep generating stuff like that. Or next thing should be multiplication of A and B, for example. And theorem provers could take the program state at that point and decide whether this program state can anyway be completed, whether this program, the half completed program, this program while still satisfying your high level specification, right? If there's no such way, then you can immediately call BS, saying this is not going to work out, and ask ChatGPT or someone to backtrack, right? Or not ChatGPT, sort of language model, like to backtrack, right? So that was the idea, and we've put this into use in SQL synthesis, SQL program synthesis. So far the results are quite promising. We're still working on it. It's not yet done. So hopefully the paper will be out in like 2-3 months or so. Okay, so these are the things that I wanted to talk about. Feel free to reach out to me if you have questions, or if you want to discuss some research. I see from the names here that there are a few who have written to me. I unfortunately couldn't reply to you, but if you could drop by my office as well. Like I'll be our CUPLV lab is inside CCell. I'm right now talking from inside my office. So, or if I haven't replied, please send me your email again, and I'll try and reply. The last couple of months I've been really busy. Okay, so that's it from my end. That's all I wanted to talk about structurally, like in a methodical fashion. But I'm now I can do a freewheeling chat with you if anyone have questions or so.
I have a question, Professor.
Yes.
Yeah, so I have a question on the Prajakta.
Okay, hi Prajakta. Yes.
I have a question on the second project. So basically, are you doing the AI watermarking to check whether the code is generated by LLM, or are you trying
this one? Here, no. I mean, we are not. My aim is not to stop students from using LLMs. My aim is to. So it's. I'm not trying to do and find. Oh, you have done homework. You copied. That's fine. You're in grad school, and the course I was teaching was a grad course, so they know better, right? the aim is to ensure that when they're relying on LLM to generate a solution, it better make sure that the LLM is in fact correct. It is in fact generating the solution that I actually want, right?
Okay.
So let's say, for example, I give a programming assignment. So how do I grade a programming assignment? Well, I have a set of test cases, right? I reveal my test cases to the students as well. So can the students, you could feed those test cases into ChatGPT, or you could sort of run them yourself, right? And if they fail, you could ask ChatGPT, hey, this seems to have failed. Can you generate me a new solution? But even that is not guaranteed to converge, because there is no guarantee that ChatGPT is or any language model is going to learn from its mistakes.
Yeah.
Right?
Yep.
For small examples, they tend to, but in general, they are not. So, but how do you guarantee that once you have this specification, which is in form of test cases, that anything that is generated by the language model is in fact guaranteed to satisfy these test cases? So that's the idea.
Okay.
For example.
So, Professor, the feedback that comes from the theorem provers then goes back to the LLM models. Are they modified prompts as in or something else?
Well, that's an approach. That's definitely one approach, and people have taken that approach. I think there was a paper last year in ICSE who have tried to take that approach in Python data frames code generation somewhere. But we don't. What we do is we treat LLMs not as prompt answering machines, but rather next token generating machines, right? So the language model is a matrix, right? So you feed your context into this matrix. So you get next bunch of tokens, and each token annotated with a probability, right? And so what things like ChatGPT does, it picks the token with the highest probability, adds it to the context pack, again does matrix multiplication, and gets new tokens, right? And again picks the highest probability token and adds it back and so on, right? So it's sort of greedy in that sense. So can we sort of intercept this LLM thing at this point and say, keep track of this beam. And so when you get the next token, along with the context, ask this question to the theorem prover that, hey, is there any way that I can complete this context and while still satisfying my high level specification, right? So that's the question we ask. So it happens not at the level of prompts, but at the level of tokens. That's a short answer.
Okay. Oh, all right. Thank you.
Okay. Yes, again, I think Lalit raised his hand.
So this is more of a general question I have. So, I mean, at least in cryptography, verification is either through formal proofs. We have a definition of security and go about building oracles and whatnot. But there are some models like ProVerify, I think there's one with mostly by Blanchett. Yeah, I think this is CryptoVerify, and there's also VerifyPal. But they are very restrictive, and you have to build out your own primitives, right? So I saw some probabilistic modeling.
Yeah, the problem.
Yeah. So
could you repeat?
What sort of?
I lost you. I lost you for a moment there.
Yeah, probabilistic modeling like Prism, modeling your protocol of a discrete time Markov chain, and then looking at what state would it end. That sort of stuff being done very recently. But how from a program verification PLV perspective, how do you approach this? It's very new to me, so I just want to know. Yeah.
So first of all, let me point out that ProVerif already does approach it from the PLV standpoint or from method standpoint, because ProVerif, the way you operate ProVerif is you basically encode a version of protocol right inside in ProVerif, and the formal, although ProVerif has surface level language, right? It's actually what is called a pi calculus in formal methods, right? So you encode when you're writing your protocol in ProVerif, you're in fact writing a specification in pi calculus, and once it has a specification in pi calculus, it sort of has a bunch of rules that it uses to analyze that specification. And all of those rules are symbolic. I mean, it assumes perfect cryptography and all of those things. So and the proof is in fact a hard proof in the sense that you actually, when ProVerif tells you that let's say some certain message M is going to be secret, then that means that in the symbolic model there exists a proof for that this K, whatever it was marked as secret, has no path to go to attack it, right? So that was the proof that is actually done behind the screens in ProVerif, right? So that is a very symbolic the PL verification style proofs. But also computational model, the CryptoGraph or EasyCrypt, whatever you take, right? So they are based on, as you mentioned, oracles. Well, yes, oracles as in the hardness of problems like Diffie-Hellman or something like that, right? So you basically show something is safe by reducing it to the hardness problem, Diffie-Hellman or whatever. And these proofs can again be rigorous, and they can be automated. Can be, although it's not easy to automate them. So they are done. For example, CryptoVerif is CryptoVerif or is it EasyCrypt? I don't know. I remember one of them is basically a tool embedded inside Coq, which is what I've shown on the screen here, right? So it's actually a framework that is embedded inside a theorem prover. So your reductions, your computational proofs are actually done by symbolic manipulation inside theorem provers like Coq and Lean, using the theory of probability, using your measured theoretic probability. I hope that makes sense.
Yeah. Yeah, is this like TLA plus to an extent, at least the Coq part?
Coq is not TLA. So are you aware of Universal Composability Framework, UC?
Yeah.
Okay. Okay. So if you're doing a proof in UC, for example,
yeah,
right? It's a full proof, right? It's not model checking or testing things. You're actually have to show that your real protocol is indistinguishable from ideal protocol.
Yeah.
Right. So that proof, whatever you do, it's a mathematical proof. But if you do it on using pen and paper, that might be incorrect, right? So who is to say? You might have convinced yourself that the proof is correct, but you don't know, right? Or even if you might have shown it to your friends, and your friends might have already been convinced, but who knows? So theorem provers like Coq, Lean, and Upstart, so they let you. They are symbolic provers in the sense that they let you do proofs, but if ever commit a logical error, they immediately catch it, right? So there's no way you can convince these theorem provers with an incorrect proof, by the virtue of them having this symbolic foundations. So those are theorem provers in the sense they help you do the proof and check the proof that in fact it is in fact a correct proof. What we tend to work on is, okay, people can do manual proofs, but they don't want to. So how do you sort of make it more automatic, this process more automatic, so that you can generate mathematical proof sort of automatically?
Makes sense. I mean, it's like you build, your whatever assumptions you have and start building over your proof system, right? So here you're trying to automate that. Instead of me writing a truth statement, I would rather just give my program or something more, not too much, to quickly show that this program really does what I want.
Yes. So exactly. So how do you show that? What is the logic used to show that? All of that is, the research.
The complex. Yeah.
Any more questions?
Interesting.
Okay. Evan, would you like to take over? Hello? Evan, you're muted. Okay.
Sorry, Zoom snafus.
Okay.
I'm here in the CUPLV lab with CK, current student. Happy to take questions and join the conversation.
Yeah, let me stop this screen sharing so that we can actually see our faces.
So I guess I could give a brief intro. Is that what you'd like me to do, or Gautam?
Yeah, yes, please go ahead. I see as per the program that you're supposed to take over after me. I have not much idea of what is the first plan.
Oh yeah. So hi, I'm Evan Cheng. I'm one of the faculty members here in the CUPLV group. With an office across the way from Gotham. I primarily work on proving properties of large-scale software systems, One of my recent PhD students did a bunch of work on Android and essentially improving Android systems. Working with Gotham with another student on verifying distributed systems, again with a sort of real code that developers would actually care about, right, if you will. We have proofs of like protocols, but how do we make them work when they're actually implemented in code? So yeah, so that's kind of the high level bit about me. I see we also invited some PhD students here to kind of for you to potentially pick their brain about what it's like to do PhD student stuff. So maybe I let them give their intro.
Yep. Hey everyone, my name is Chandrakant. I work in the CUPLV lab. My advisor is Sriram Shankar, and my research primarily focuses in the intersection of theoretical machine learning and dynamical systems. So we're kind of looking at how can we build predictive models for systems that are governed by ODEs, for example. So yeah, verifying those systems, getting guarantees of the systems, that's where my research currently lies. So yep.
And I'll chime in real quick. Hi, everyone. My name is Kirby Linville. I'm one of the other PhD students at CUPLV. I'm advised by Gautam Kaki. My research, I think Gautam introduced it. I just caught the tail end, but it looks like he was talking about it a little bit, where my research is focused on verifying privacy properties for protocols. And so as Gautam mentioned, there are some existing approaches to do this, but the existing approaches tend to either not capture enough detail to verify the kind of properties we want to, or require too much effort. So we're looking at what assumptions can we make to simplify that proof effort while still structuring the language in such a way that we can get some more precise guarantees. And then I also help with a few other projects. And so I think Gautam also mentioned the LLM-driven synthesis. And so both CK and myself are helping with that project too. So if you have any questions about any of that or just life in CUPLV, we're super happy to answer those.
More questions?
I guess in lieu of questions, it might help to talk a little bit more about what CUPLV kind of is. I don't know if you introduced that, Gautam.
Oh, I've actually no. That was done. I've given this
Perfect
presentation. So
awesome.
Yeah. So we have this. So maybe this is perhaps the key slide. So if you have anything that you want to talk about, any of these things, feel free to raise your hand.
Yeah, this is a good time to ask questions. All of us are here. So if you have any doubts about like any work that we do, yeah, feel free to shoot us a question.
Like we can go into some breakout rooms if you like, so that we can have a smaller group conversation, learn a little bit about you.
Can we breakout rooms? I'm creating 4.
Cool. And then just to give you a little bit more context about our backgrounds. So I think both CK and I worked in industry for a little while before going back to school. I went straight into the PhD program. I'm in my 5th year now. CK first did a master's here and then transitioned to a PhD. So if you have any questions about those experiences or are considering those yourself, feel free to pick a breakout room based off of your interest there.
All right, we'll jump in.
Hi, I got dropped from the call, so can I be pulled into any of the breakout rooms?
Do you want to go back to where you were?
Yeah,
Okay, hold on.
breakout room 1. Yeah, room number.
Sorry, I didn't know if you left.
All right. I sort of closed out and left the breakout room. I guess are we been about time?
I think Gotham jumped off.
Okay. All right. Thanks, Megan, for organizing this.
All
Yeah.
right, thank you.
Thank you. Thanks, everyone.
Thank you.